welcome everyone to the last BHI Colloquium, and it's very fitting that we hear from Ido about the observations of the LIGO source of the two neutron stars. Just a brief, well, first of all, after this talk, at 3 p.m. we will have a party, a winter party, to celebrate the successful year and a half that we had at the BHI so far. Then we will start the events again towards the end of January. The
23rd is the
23rd is the next meeting. So I wish everyone happy holidays. Just an anecdote, I woke up at 3:30 a.m. this morning because it all boils down to something that I mentioned 2 weeks ago, this peculiar object that is passing through the solar system. And so this object that is elongated with an axis ratio of 1 to 10. And so a couple of days after I mentioned it here, I wrote an email to Yuri Milner about it, just telling him, look, this is a very unusual object, the first interstellar object to be detected in the solar system, and it's very peculiar. We've never seen something like that as an asteroid. And a day later, his assistant sends me an email and says he would like to meet with me for an hour. So I was about to go there anyway to Palo Alto, and so I met with him, and then he decided that we use the radio telescopes, the Green Bank telescope, to check for any radio transmission from this object. So I said, okay, well, why not? You know, I mean, obviously, a conservative person would say there is zero chance that there will be, but if it's a probe sent by an alien civilization, you know, that's one form of SETI, looking at any radio emission from it. So he said, we'll do that, and then 2 days ago, a bunch of reporters started chasing, like asking about it, because we are planning to do it tomorrow. And so at 3 a.m. it was the BBC. I mean, yesterday it was Newsweek and Washington Post, and this morning a few radio stations, and now just half an hour ago CNN, and so it becomes a story that astronomers are using a large radio telescope to check if this piece of rock may have any transmitter on it. By the way, the Greenback telescope is sensitive to a cell phone at a distance of 2 astronomical units. So, just an anecdote. And then I'll let Michael introduce Ido.
Great. Well, I'm delighted to introduce Ido Berger, our speaker today for this special colloquium. So Ido is a professor here at Harvard University, and he leads really a large and incredibly productive group that's studying all sorts of optical transients, supernovae, gamma ray bursts, tidal disruption events, and so forth. And in particular, he and his team led a number of observations on this recent neutron star merger detected by LIGO, finding the follow-up and this first detailed study of a kilonova, all the way from UV through optical and infrared and radio. So today he'll tell us about this incredible event and this new future direction of astronomy, really.
Yeah. Well, thanks for having me, and it still amazes me 2 months or 4 months now after this event happened, and 2 months after the announcement was made that we've been able to do the work that I'll tell you about today. It's something that I think a lot of people have been waiting for a long time, to see electromagnetic radiation from gravitational wave sources, let alone just seeing gravitational wave sources to begin with, but then to see electromagnetic radiation. And I think the really remarkable thing with this event is that the richness of the data that was collected and the enormous power that it gives us to interpret the system, both by looking at the gravitational wave signatures and the electromagnetic signatures. So I think this is really the first step in what is now certain to be a significant field in observational and theoretical astronomy for decades to come. The gravitational wave detectors are only going to improve, and the number of sources that are detected will go up significantly, with the expectations that by the end of the decade we may have one of these events happening every couple of weeks, which is kind of terrifying, to be honest. A lot of the work that I'll talk about was done here at Harvard and by some of my current students and postdocs and former people in my group. So if you want to find out more, you have a lot of people around here who were directly involved in this study and have carried out the observations and can tell you a lot more about what's happening. So this was kind of an interesting occurrence for me. I've never seen anything like this where you collect all this information and you analyze it, but you're not allowed to publish it until LIGO tells you that the embargo is lifted. And so we carried out a series of observations following up this event, and we wrote all of our papers, and then we just waited for October 16th, which was the day the discovery was announced. And so our papers, we wrote a series of 8 papers covering all possible aspects of this event, from the discovery of the optical counterpart through follow-up spectroscopic observations, radio and X-rays, studies of the galaxy where this happened, and a comparison of this event to short GRBs. And all of these papers appeared in the special issue of the AppJ Letters on October 16th. So, and then there were a couple of other papers that had a combination of LIGO and electromagnetic information that had both the LIGO collaboration and people from our group and other groups. So this first one on top here is that infamous paper that has 3,800 authors, which was quite an incredible undertaking. And I encourage you to read it. It kind of reads like it was written by 3,800 people. But it attempts to kind of capture the overall story from discovery to some very basic interpretation. And then we've been going at it since then. Some of the results I'll show you today are new observations of the system, so it's still observed in radio and X-rays, and so there will be additional papers that will come up over the years, months and potentially years. There's this website that we put together called kilonova.org that has all the papers and all the data, and you can get access to this. A lot of PR materials and things like that. So it's fun to look at. So in addition to we had 8 papers from our group. There were over 45 additional papers that came out on that day. And by now, if you just look on ADS for GW 170817, which is the name of this event, there are over 130 papers that have been written on this object since October. So it's quite remarkable. And so, one could ask why so much excitement about one astronomical event. And I think that it represents so many firsts and things that people have been thinking about for a long time, that there's really a lot of enthusiasm around this. It's really remarkable. So it's the first time we've seen gravitational waves from a binary neutron star merger, the first time we've seen gravitational waves and light from the same source, first confirmation that gamma ray bursts, short gamma ray bursts come from binary neutron star mergers, that nucleosynthesis of the heaviest elements actually occurs in these systems and not in supernovae, and so on and so forth.
Is there direct evidence that it's our process? There could be another energy source in principle.
So I'll talk about this. I think both from the energy input rate and from the opacities, it's pretty clear that it's our process and not something else. The other part that I find particularly remarkable is that this one event also brings together all these completely disparate areas of physics and astronomy that don't usually talk to each other. So we have things like gravity and general relativity that come in from the gravitational wave side of this, nuclear physics when it comes to the nucleosynthesis and the equation of state of neutron stars, atomic physics, which are important for understanding the opacities of these materials, high energy astrophysics in the context of gamma ray bursts, stellar and binary evolution in terms of how a system like that actually comes into being and how it evolves, and even cosmology in measuring the Hubble constant with these kind of sources. And there's actually a paper on measuring the Hubble constant with this one event. That measurement is not particularly competitive, but still it demonstrates this. So I think there's just a confluence of a lot of physics that comes into these studies, which makes it particularly challenging and exciting at the same time. Okay, so what I'm going to try to cover today, and please feel free to jump in with questions, and don't wait until the end. is why we actually want to find EM counterparts and what we can learn from them, and a little bit about what we thought we understood about EM counterparts based on observations of short GRBs, and why we thought that they were neutron star binary mergers, and then what we can learn about this event from the wealth of data going all the way from radio to X-rays. Okay, so why do we even care about finding electromagnetic counterparts to gravitational wave sources? Isn't it enough to just detect gravitational waves? And there are several fundamental reasons that we want to connect these two sets of two carriers of information. The first one is that gravitational waves can be detected with LIGO, but the sources cannot be localized precisely on the sky. And so if we want to have a precise position, which therefore can give us a precise distance and an understanding of what kind of galaxy the event happened in and what kind of stellar populations it's associated with, we need much more precise positions than what we can get from gravitational waves, and we can get that from electromagnetic counterparts. The other important part is we can learn about what happens after the merger. So the gravitational wave signal tells us what happens in the final moments in the evolution of this binary system up to the merger, and perhaps with some events that are detected at high significance, what happens shortly after the merger. But if we want to understand what happens to material that was part of the neutron stars after the merger, is any of it ejected? Does all of it fall into a black hole? Do we have a relativistic outflow? All of that information comes from electromagnetic information, not from the gravitational wave signal, including things like what is the nature of the remnant? Does a merger of a neutron star binary lead to just a more massive neutron star? Does it lead to a black hole immediately? Or does it lead to an outcome where there's first a neutron star that then collapses to a black hole? So that kind of information is imprinted in the electromagnetic signals.
Can we see the X-rays from the black hole?
Not right now.
Because there was a paper today about that.
Yeah, and I think that paper is wrong.
It's wrong.
Yeah, I'll come back to that towards the end. There's been a lot of activity on the X-ray side. Yeah. One could look at different processes that happen in neutron star binary mergers and come up with different ideas of what kind of electromagnetic signals we could expect. One possibility is a relativistic jet that comes out along the angular momentum axis, and that's been discussed in the literature for at least 20 or 30 years. So that's an idea that's relatively old. So the idea is that there will be a gamma ray burst along the axis. But of course, that might not be visible if we're looking at the system from a different angle. There's also an expectation that some material will be ejected roughly isotropically during the merger itself, material that was part of the neutron stars. And that could power optical and infrared emission. And all of these components will interact with the surrounding medium and produce radio and X-ray emission as well. So the idea is that there is actually quite a lot of different possibilities. Some electromagnetic signatures will be isotropic, some will be beam, some will be relativistic, some non-relativistic. They will essentially span the full electromagnetic spectrum. And I think the remarkable thing with this event is that it essentially showed all of these. And partly, I think, because it's very nearby, but it just shows that we're kind of on the right track, and there are all these different possibilities, and it seems like nature actually does produce all of these in these mergers. Okay, so I mentioned short gamma ray bursts. So the idea that short gamma ray bursts could be powered by neutron star binary mergers has been around for a long time, but it was mainly kind of based on basic theoretical arguments without a lot of observational evidence. But over the last 10 years or so, we've spent a lot of time and effort following up short gamma ray bursts that were found primarily by the Swift gamma ray mission, and have started to collect information that suggested that that is really the correct picture, that they really do come from neutron star binary mergers. And that has to do with the fact that they at least sometimes come from elliptical galaxies that have no star formation. They are not associated with supernova explosions. They seem to be to have a broad distribution of where they're located within their galaxies. Some are close to the center, but a lot of them happen far away from the centers of their galaxies. So it seems like they have the experienced kicks that are expected in both single and binary neutron stars. And from observations of their afterglow emissions, so observations from radio to X-rays following up on short gamma ray bursts, we found that their energy scale is about 10 to the 50 ergs, and they happen in fairly low density environments. And they're collimated in jets with an opening angle of about 10 degrees. Okay, so those numbers will come into play when we try to interpret the observations from this particular event. But overall, it seems like all the observations we had were pointing to gamma ray bursts being, short gamma ray bursts being one manifestation of neutron star binary mergers. Of course, for none of these we had actual LIGO detections. So we didn't know for sure, but all of the observational evidence seemed to point in that direction. Now, all of these gamma ray bursts that we've been looking at were at much larger distances. So in fact, none of these would have been detected by advanced LIGO, even when it reaches design sensitivity. The nearest one is still a factor of several times beyond the reach of LIGO. So it's a somewhat different population just because of the distance scale.
You know, there is material ejected from these events.
Yeah.
And it's a percent of a solar mass or something of that magnitude. Wouldn't it make a bigger density than the one you mentioned here?
So the density here is the density, the pre-existing medium around these systems that the relativistic jet encounters. So the material that's flowing at slower velocities is lagging behind, and it's not part of that density. And I think this density is more reflective of the fact that generally these systems are further out in their galaxies than the interstellar medium. Now there was one interesting gamma ray burst from 2013 that showed excess infrared emission at late time. So what I'm showing here is brightness as a function of time, and you can see the afterglow fading away in visible light and infrared. And then about 10 days later, there's observation with a Hubble Space Telescope that shows this excess infrared light. And it's one data point, but that's been interpreted as the signature of nucleosynthesis, heat input from nucleosynthesis that happens in the merger ejecta. So I'm going to talk a lot about this idea. This is what's been termed a kilonova, is kind of a name for that emission. And so this was our kind of best case of a kilonova before the event I'm going to tell you about, essentially one data point.
Either why wasn't that follow-up later for more than
we tried and we asked for more time and we got turned down. So it was a bit short-sighted by the director. Yeah. Okay. So let's talk about this kilonova, because again, the idea with the relativistic jet is that we might be able to see it if we're roughly aligned with the jet, but if we're very far off axis, we might not see it. On the other hand, there's this idea of a kilonova, which is a more isotropic counterpart that we should be able to see from all directions. So what is this kilonova? So the idea here is that during the merger of two neutron stars, some material will be ejected, either in tidal tails that you can see in the simulations, or through winds that come off an accretion disk that forms after the merger, and even in the actual shock-heated interface in the collision itself between the two neutron stars. And that material is expected to be neutron-rich and to expand away and undergo nucleosynthesis, and the radioactive decay of that material should then produce energy input that will be observable as light. So the reason this is interesting is that both the presence of these components and how much mass is ejected and the velocity depends on the properties of the merging object, so whether we have two neutron star or a neutron star and a black hole and what the mass ratio is. And it also depends on the nature of the remnant, whether there's prompt formation of a black hole or a delayed formation of a black hole, or a stable neutron star, as well as on the details of the nucleosynthesis. So if we can observe the signature of these different processes, the observational signature, then we can back out in very basic information, fundamental information about the system, its outcome, and the nucleosynthesis.
You know, free neutrons decay after 10 minutes or so.
Yeah.
So is there anything expected after 10 minutes?
Yeah, so in principle, if some of the material is traveling rapidly enough that it doesn't undergo nucleosynthesis and it just free neutrons, then they should decay and produce quite a lot of heat. In this particular event, the first observation started about 12 hours after the merger. That. So if anything like that happened, we missed it.
But it could happen.
It could happen. Brian Metzger has a paper, I think from a couple of years ago, showing expected light curves, and essentially the duration of that signal is of order an hour or something like that. So it's very prompt. Okay, so people have been studying these systems in the context of nucleosynthesis for a while, and essentially doing simulations that track the ejected material and its properties. And so this is a movie tracking trajectories of material that's ejected in a neutron star binary merger and following the nucleosynthesis. And the idea is that early on there's formation of some light seed nuclei, which you can see here. And then because of the very high...
Sorry, what are the axes?
Yeah.
So this is number of protons versus total number, atomic number.
Is there time here as well?
So time is flowing up here at the top. Yes, it's 1 second, 10 seconds, 100 seconds, and so on. So the idea is that so there are seed nuclei. There's a high flux of neutrons that are captured on these seed nuclei very rapidly. So that's why it's called the R process, the rapid process. And then these unstable isotopes will decay to the island of beta stability. And as they decay, they produce energy that can then be seen as visible or infrared light. Okay, so let's just see this one more time. There are a couple of things to point out. One is that the process itself is rapid. So the initial formation takes of order a second, and then it's essentially just decay of these elements. And so you can see that the blue points here are the solar abundances going to high atomic numbers. And you can see that the material that forms here actually matches really well to the solar abundances. So it suggests that neutron star binaries could be the production site for these heavy elements. And then this decay takes place, it essentially leads to kind of power law energy input. So it starts after about a second and it then goes on indefinitely. So these simulations that people have done with different mass ratios and equations of state and things like that, varying a variety of parameters, suggested that somewhere between 10 to the minus 3 and maybe up to a tenth of a solar mass of this material can be ejected in a neutron star binary merger. Okay, so there was quite a wide range of possibilities. Now, the final important ingredient in terms of understanding the manifestation of this as an observable signature is how opaque the material is to radiation. So these radioactive decays don't produce optical photons or infrared photons. They produce alpha particles and beta particles and fission products, but that energy cannot escape. It gets thermalized by the large optical depth of the material and then eventually escapes as optical or infrared light. So depending on how opaque the material is, it can be viewed as a very different observational signature. Okay, so what's shown here is the opacity of iron peak elements, okay, which dominate in supernovae, for example. So they're very high in the ultraviolet, and then the opacity becomes very low. So when we look at supernovae, their emission in the ultraviolet is suppressed because of this high opacity, and most of the radiation comes out in the optical part of the spectrum. But for some of these heavy elements, these R process elements in particular, lanthanides, the opacities can be very high, all the way from ultraviolet into the infrared, which means that they tend to be opaque even in the visible part of the spectrum. And if a lot of these lanthanides are present, then the emission will be dominated in the infrared instead of in the visible part of the spectrum.
Does depend on the temperature. Is this the core material? You don't care about the temperature?
I think this is calculated at the temperatures that are appropriate for these systems. Okay, so people have used this to calculate and predict what the light curves are going to look like, essentially what their brightness as a function of time is going to look like. So you take the heating rate that comes from R process radioactive decay, the opacities for R process nuclei, the ejecta masses and velocities from numerical simulations, you put it all together and you can predict what these events are going to look like. So the focus has been on kind of taking two limiting cases. One is where lanthanides are present, and the other one's when they're absent. So when they're present, what you can see here, so it's brightness as a function of time, and going from ultraviolet to infrared. So when lanthanides are present, most of the emission comes out in the infrared. So infrared is bright, ultraviolet is very dim. And you can see that the signature lasts for about 10 days or so. If there are no lanthanides, so this is called a red kilonova because most of the emission comes out in the red part of the spectrum. If there are no lanthanides, then now you can see that the ultraviolet is not suppressed. Most of the emission comes out in the visible part of the spectrum, and it's dimmer in the infrared. So that's been called a blue kilonova. And here, because the material becomes transparent much earlier, it fades away more quickly as well. So it tends to be somewhat brighter, but it fades away after a day or two. So those were kind of the two possibilities that people were thinking about. That the counterpart is either going to last for a day or two and be blue in color, or it's going to last for a week or 10 days or a couple of weeks and be red in color. Okay, so the challenge for us as observers is to try to find something like this that's faint and it fades away very rapidly. Even in the case when it lasts for a week or two, that's still much less than a supernova. And then we have to look in these big LIGO regions on the sky to try to find something like that. So the way my group has been approaching this is, so, you know, what you need is a big telescope, right, that has a wide field of view, and that you can use to cover these large areas in the sky and to go very deep and do it rapidly. So we've been using an instrument called the Dark Energy Camera on the Blanco 4-meter telescope in Chile. So that's an instrument that was built to do the dark energy survey, but we're using it for a very different purpose. And the idea behind this program was that we search these large areas on the sky rapidly, try to identify the counterpart, this kilonova, and then once we identify it, then we can use a lot of other telescopes that have a very narrow field of view to study that object in great detail. So we can get optical infrared spectra, and we can get radio and millimeter observations, X-ray observations, and so on, with instruments that have no way of covering the entire region on the sky. So prior to this event, we actually did this 3 times for LIGO black hole binaries, even though we did not expect to see any electromagnetic radiation from black hole binaries. It was just a lot of fun to do, and we kind of checked if we can actually carry out these kind of observations and analyze the data. And
you must have confusion with other transients.
Yeah, so part of the work there was done on how do we reject. When you look at such a large area in the sky, there are going to be a lot of other sources that are unrelated. How do you reject them and make sure that they don't interfere? And we've done the same here, and I'll show you. Okay, so then we had finally a neutron star binary to follow up. GW 170817, which the name indicates when it was detected, August 17th of 2017. And you can see the gravitational wave detections here. It's the loudest signal that LIGO has detected so far, so it's quite a significant event. And from this information, in addition to other things, but from this information, it's possible to determine the masses of the two objects in the binary. So in the case of low spin, the mass of the more massive object is somewhere between 1.4 and 1.6 solar masses, and the lighter one is between 1.2 and 1.4 solar masses, with a final combined mass of 2.74 solar masses. Okay.
It was detected at Virgo, right?
It was, I think, only very marginally, like 2 signals.
Well, the scenario was 2, roughly. So Virgo did not help for detection, but I guess you would say it will help for sky localization. Yeah. So it was extremely marginal here. But consistently with the PSD of Virgo, that was pretty bad.
The detection is done at the time when the masses, non-neutron matter is being lost, or is it after some could have been lost? So when they determine the masses, are these the masses originally of the binary, or are these masses minus the material that was kicked out?
I think that, so we have, separate from this, we have an estimate of how much material was ejected.
Because it could be time-dependent, the mass.
Yeah, it could be, but I think the amount that was ejected was a few hundredths of the solar mass, so it's not a big perturbation on this number. But
second significant digit is not significant.
Yeah, but I don't know.
In our model, there is no time dependence.
No time dependence.
These are the masses at minus infinity if you want.
So you cannot tell if there is time, or can you? Can you see that if the mass was evolving, can you tell?
Well, if you have a way of parameterize that in a waveform, we can try. My guess is that it will not be measurable.
But it would be interesting to check.
Theoretically, it's possible.
Since Ido said that it can go up to 0.1 solar masses, it's interesting to check.
Yeah, but the second digit, I mean, you haven't, though the uncertainty is on the first digit there, right?
But not for the total mass.
For the total mass, it's also.
Total mass is also pretty uncertain. What we do best is the Chern mass. Yeah. The Chern mass is at the 4th decimal.
And what's the precision for the total mass?
I think it's still at the 1st decimal. Do you
I don't remember the formula.
No, go ahead.
Is there a degeneracy between the equation of state and the change in mass? Because then there could
in
be
the gravitational wave
there
signal,
could be a spin dependence on, or there could be a spin dependence of the amount of matter.
Yeah, that's what it's showing with the two colors there.
Yeah, so I think realistically, at the level of how much ejecta we infer from the EM signal, I think it's going to be hard to determine that just from the gravitational wave data. Now, one thing that's interesting is there's this parameter called the tidal deformability, which is related to whether the objects are point masses or actually have a size, finite size to them, and therefore is a parameter that's interesting to measure for neutron stars in particular and is related to the equation of state. So here, at least with the analysis that's been published so far, there's only an upper bound on that, which means that from the gravitational wave data alone, it's not possible to tell whether these objects are actually neutron stars. And it's also not possible to tell what the final object is. We know its mass, but it's not clear whether that's a black hole or a neutron star. And it's not clear whether the two objects are neutron stars to begin with. So that's kind of a degeneracy that's left open by the gravitational wave data. But as I'll show you, we can address this question from electromagnetic data, which is, again, another interesting, as I mentioned, that's one of the things we want to do with electromagnetic data, is understand the nature of the system. Okay, so this event was detected and announced shortly thereafter, and a few hours later, there was a first map on the sky that was produced by LIGO and Virgo. So what's shown here in the blue banana-shaped regions are the localization just from the two LIGO detectors. And then in green is the region that includes the Virgo information. So even though it wasn't detected particularly strongly in the Virgo detector, the lack of a detection helped to localize them on the sky because it was in a region of the sky where Virgo had low sensitivity.
So when you found the actual E&M counterpart, were you able to backtrack and, in some sense, refine the localization from just the GW detectors?
Oh yeah, by a huge amount, right?
No, but I mean, in the future, would they be able to give you a smaller window from what they learned from where it actually was in their error?
In terms of the systematics.
Yeah,
I'm not sure.
No, it's statistical dominated. There's no systematics.
Oh, it's all statistics.
Okay, so there was a map that was available within a few hours. Now, this just when the source was detected, the location on the sky was still in daytime, and so it was not observable for another 11 hours or so. 10 hours.
Or X-rays.
Except for gamma rays, yeah, or X-rays or radio for that matter. But so at least from the point of view of doing optical follow-up, we had to wait about 10 or 11 hours. So this delay in getting the map of a few hours was not a big issue.
Why does it take so much time?
It was peculiar to this event.
They can give it to you.
Yeah,
That's humans. Yeah. That's us being on a teleconference for hours before the
In
site.
principle, he might want to look at it 10 minutes after you did.
We had it. I mean, you have the time there. We had it pretty quickly.
Yeah, but it wasn't.
So I think here there were. I don't want to get too much into the peculiarities of why there was a delay. It's not something that's built into the LIGO analysis or anything like that. So in the past we've gotten maps much more quickly.
Why hasn't any Asian telescope got it?
Yeah, that was my question. Like, it must have been night somewhere.
Yeah, well, so it's
as far as I know, right?
No,
in the
right hemisphere.
Yeah, so it's the location of the sky, declination of -25. So it was visible from South Africa before, but I think that was as when this first map came in, it was already setting there.
Or HST.
I mean, the problem is that this location is very close to the sun, as I'll show you in a second. So in any case, the localization came in at declination of -25, right ascension of 13, with an area of only 30 square degrees. So all the previous detections of black hole binaries were a few hundred square degrees. And here, thanks to the detection with 3 detectors, it was a pretty small area in the sky, and also there was a distance estimate, somewhere between 25 and 50 megaparsecs.
Isn't that more significant because the volume is so much smaller than previous?
Yeah, the volume is smaller, but
so it's
just
not so
even
much the area. I mean, the area is a factor of 10 smaller, but the volume is much smaller because of the distance.
Yes, no, definitely. But again, even if from the point of view of just trying to cover the whole area, it was finally manageable for the first time. Okay, so it was a bit of a near miss. So LIGO just turned on 3 weeks earlier, and 10 days later, both Virgo and LIGO shut down for the end of the second observing run. So this happened at exactly the kind of right moment in time when all the detectors were operating. But also, as I mentioned, it was very close to the sun. So if this was located another kind of 1 hour in right ascension further to the west, it would have been too close to the sun to follow up in the optical. And the point is that the only way to follow up these wide areas on the sky is in the optical. In the radio, X-rays, we don't have the possibility of doing that. I mean, gamma rays is the other possibility. Okay, so talking about gamma rays, so there was also a gamma ray burst associated with this event. So independent of the LIGO detection, Fermi, the Fermi gamma ray satellite, detected a source about 2 seconds after the gravitational wave event. The merger happened, but announced it earlier. So automatically announced it within 14 seconds of detection. So this is the gamma ray burst. It's fairly weak, but you can see it's clearly detected. And this is the time of the merger. So there's almost a 2-second delay between the merger and the onset of the gamma ray emission. It was a very weak gamma ray burst, and given that it was so nearby, the energy was only about 10 to the 46 ergs. Okay, so in terms of the gamma ray burst, the 2-second delay is still a bit of an open question of what the cause of that is, and depending on what model people take for what produced the gamma ray emission, they have different explanations for why there is this delay. The amount of energy is about 100,000 times lower than a typical short gamma ray burst. Okay, so clearly we're seeing something different. It's not exactly what we see when we see a typical gamma ray burst. And there are different ways of explaining that. One is that we're looking at a jet sideways, so we're not exactly seeing it exactly down the barrel of the jet, so the emission is much weaker. Then we're looking at a jet that has some structure to it, so usually when we see gamma ray bursts, we look down the energetic core of the jet, but in this case we looked on kind of the wings of the jet, and so the emission is much weaker. Or maybe that there is some other component altogether, something that people call a cocoon. When we see a gamma ray burst, we see the jet, but here we're looking sideways and we're seeing this other component that is much lower in its energy content. Okay. It's hard from the gamma ray emission itself to distinguish between these possibilities, and I think from the radio and X-ray observations, there's still a lot of debate about whether we're seeing that or that. I think we can rule out this possibility now. Okay, so there was the gamma ray burst and the gravitational wave source both detected that caused a lot of excitement. One thing I forgot to mention is the gamma ray burst was much more poorly localized than the gravitational wave source. So initially, when the gamma ray burst came in with a map, nobody was paying attention to that because Fermi finds a lot of these gamma ray bursts. None of them are followed up. The localization of the sky was almost 1,000 square degrees. So it did not stand out as anything unusual. It wasn't until the LIGO detection came in that it became obvious that this was an exciting event. Okay, so for us, the idea was we had this map within a few hours, and we still had to wait another 7 hours or so before we could observe that part of the sky from Chile. But as soon as the sun set in Chile, we started observing this region with our telescope. So you can see these red markings here are the pointings of the telescope. So for the first time, we could very rapidly, within less than an hour, cover the whole region. Okay. And now there was a bit of a wrinkle, and while we're almost done with the observations, suddenly we got a revised map from LIGO. So that's the dashed lines here are the revised map, and the white lines are the original map. So in the original map, we designed it so that we could cover almost the whole thing, 93%, but then they shifted the map on us, and we covered, at the end, 80% of the region. But in any case, we covered it very rapidly, and as the images were coming from the telescope, we started looking at them and trying to find a new, the counterpart, a new source.
I'm just curious, why is there such significant overlap between the different tilings?
Oh, the idea, because there are, so this is shown just as the outline, but there are actual gaps between the CCDs and the detectors, so the idea was to do shifts to cover those gaps.
By half a CCD
yeah, something like that, yeah. We wanted to really cover as much as we could and not worry about gaps. Okay, so the images were coming off the telescope, and one of the things that were obvious is this is a nearby event, and the volume is relatively small. And so initially, we just looked around the locations of where we knew that there are bright galaxies at the right distance scale. And so going through that process, eventually, one of my colleagues, Ryan Chornock at Ohio University, sent all of us this email, and I'm not going to read it out loud, but he said, check out NGC 4993, attached is tonight's image, plus a pre-existing image. Okay.
So how many galaxies were in that void?
So there are about 50 galaxies or so.
Only 50?
Yeah.
So it's not a lot. You didn't need to tile the entire thing.
Yeah, but we had no idea whether it could come from very far outside of those galaxies. And in the case of GRBs, we see some of them happening hundreds of kiloparsecs away. And if you only image around the galaxy, you might miss the source. But it is true that some people using small telescopes looking individually just at the 50 galaxies also found the source. So for this case, it wasn't particularly necessary. I think in the future, when the distances are larger, then the volume grows as the distance cubed, it becomes more of an issue.
Just out of curiosity, what is the feature of this dark energy camera that makes it particularly good for this?
Wide field of view and the fact that it's on a 4-meter telescope.
Is it multi-wavelength continuum?
No, I mean it's the usual optical imager, so it has different filters. Yeah. Okay, so so here's what he sent us. So this was the image that we just took, and this was an archival image from Pan-STARRS of that same part of the sky. You can see that there's a new source here that wasn't there before. It's pretty obvious. You can see it by eye. You don't even need to do very sophisticated image analysis or anything like that. It doesn't mean that it's always going to be the case that that's how it shows up, and I think none of us really expected that it would be this easy.
What's the separation in kiloparsecs?
So this is about close to 2.5 kiloparsecs from the center.
Pretty close.
Yeah.
Sorry, is that the sun in the middle?
No, that's the galaxy.
Oh, okay.
Yeah. So that's the galaxy that it's in, and that is the new source. Okay. And all the other things are unrelated foreground stars. Yeah. Okay, so it popped out of nowhere, and then here's the first set of images, and then 2 weeks later, it was gone. Okay, so it appeared quickly, it disappeared very quickly, much faster than a supernova would fade away. So it kind of matched this idea that we're looking for something that had a very short duration.
Sorry, just to put this in perspective for the future, suppose this is a factor of 2 farther away, okay, like in 3, and it's at the center of the galaxy. Will you see it with image subtraction, or it's...
Yeah, but you wouldn't see it in this... So if something that's twice the distance would have a volume that's 8 times larger. So instead of 50 galaxies, there would be 400 galaxies to look at. So I think that is no longer feasible as a technique for doing this. There are just too many galaxies. So there we would just image the whole region, do image subtraction.
Okay, so what is the maximum kind of luminosity contrast between the galaxy and the object that you can resolve with image subtraction? So the order of 1 to 10 or 1 to 1,000?
Yeah, no, I mean, better than 1 to 10, not as good as 1 to 1,000. Yeah, it will depend on, of course, how close it is to the sun. Okay, so clearly, we could identify this object by eye, but one of the things we wanted to do is just make sure that there was nothing else that could match our criteria for what we were looking at. So to give you a sense of the scale of the problem of finding unrelated events, so we looked at every single detection. So here we did image subtraction. We took images that had no object flux in them, and we subtracted our original search images from them. And we found 1,500 candidates in an area that's 60 square degrees. Okay? And so that's every single thing that shows up when you subtract the 2 images. Right? So a lot of it is non-astrophysical noise from the detector and things like that. So we did a few cuts on that, and so we narrowed it down to 81 sources that were real astrophysical sources that showed variability. So these are supernovae and AGN that are completely unrelated to the event. Okay, so there's more than 1 per square degree. So when you search 100 square degrees, you have 100 sources that are unrelated to the event and only 1 that's related. And then we looked for something specifically that faded away very quickly, which is what we expect for a kilonova, but we don't expect this for an AGN or supernova. And that eliminated 80 out of the 81 and left only 1 source. And that's the source that I showed you in the previous image. Okay, so the brute force way of searching the entire area works just as well as looking around individual galaxies, and that gives me confidence that in the future we can continue to find these sources even if we can't identify them by eye looking at individual galaxies.
So I guess there are no credible models that are at odds with fading in 10 days.
caused by neutrons during merger?
Nothing really, because this, even though it's still detected in infrared, and as I'll show you over a period of a month, it just plummets in the optical like nothing that's ever been seen before. Yeah. Okay, so we identified the source very quickly after starting the observations, and then of course that was not the end of the game. That was just the beginning of the story. So here we decided to collect information all the way from radio to X-rays, and so let me talk about the kilonova component first. That's the optical and infrared. So this is the spectral energy distribution in the first 12 hours. Okay, so this is right after discovery, going all the way from ultraviolet to 1 micron, and then as it evolved over the next subsequent days. So what's remarkable is that it faded rapidly, but it also turned from looking very blue early on to very red within a few days. So remember that I told you the story where we expected it to either be very blue or be very red, depending on the presence or absence of lanthanides. Well, here we saw it start very blue and turn red over time. So I'll come back to that in a second.
So maybe the model is screwed up.
Well, things are more complicated than the simple story. The other thing is if we sum up all of the light from ultraviolet to infrared and calculate the volumetric luminosity, the total luminosity, and just track that as a function of time, we can compare that to the heating rate from 0.01 solar masses of our process ejecta and 0.1 solar masses. And you see that overall it tracks the energy input from about a few hundredths of a solar mass of our process ejecta. So it's in the right ballpark for the kind of number we expected. Now, as Avi mentioned earlier, there's this question of how do we know that the model is correct? I mean, we have this model, but how do we know that it's really correct? So one of the things we wanted to do is to take all of the data we collected. So this is brightness as a function of time from ultraviolet, which fades, you can see here, from magnitude 17 to 23. That's a factor of 100 dimming in 3 days. That's amazingly fast compared to any other transient. So it goes all the way from ultraviolet to infrared. You can see that in infrared, it fades more slowly. And we tried to compare it to models where the energy input is from radioactive decay of nickel, just like a normal supernova, and the opacities are iron peak elements, so no R process products at all. And those are the kind of models you get. Okay, it kind of fits. It just completely fails. So it turns out that there's no model that can work that doesn't have R process heating, but models that only have one kind of opacity, either blue or red, also fail. Okay, so the simplistic view that it's either going to be blue or red doesn't really work. And what does work is that you need both of these components. So you needed to have a component early on that is essentially blue, it's lanthanide free, and then a second component that has lanthanides in it that kicks up after a few days and then dominates the rest of the emission. Okay, so the model here has these two components. So it has a blue component that's 0.02 solar masses with the ejecta traveling at 30% the speed of light, and a red component that has twice the mass but is only traveling at 10% the speed of light. Okay. All right, now that was the story. So that was the data we published on October 16th. So at the same time that we published our data, all the other groups published their data, and so within a few days of that, we essentially took all of these observations and combined them together into a single data set, and we went through and checked and removed all the outliers and found that some people had systematic offsets in their data and things like that. But we combined it, so this is the full data set. It's 650 data points, which is really remarkable. We never have this kind of data for a supernova, and this event only lasted for 3 weeks or so. So it just goes to show the intensity of observations. And so with this full data set, we remodeled it, and what we found is that actually we need 3 different components of opacity. So we need a component that is, again, this blue component that has very low fraction of lanthanides. There's the component that initially we thought was high in lanthanides. The red component actually split into 2 parts. One that has a fairly low fraction but non-zero fraction of lanthanides, and one that has a very high fraction of lanthanides. And you can see the breakdown here in the different filters all the way from ultraviolet to infrared. And there's significant improvement in the fit with these 3 different components. So there are subtleties here that could not have been captured in the original models because nobody would have assumed that there would be this gradient of lanthanide fractions at this level.
is it clear that it must be three components and not a continuum, as a function of velocity or everything?
It is possible, and we don't know. Our assumption here, or these numbers are calculated assuming more or less spherical symmetry, and it's also possible that you have one component going in one direction, another component having a different geometry. So there is some uncertainty in those numbers, and could be a continuous distribution. But I think the key point being that this outflow, this material that's produced here, has this wide range of lanthanides, all the way from essentially 0 all the way up to about 10% or something in some components.
Is that opacity evolving with time, or is it just three stationary components?
Yeah, so here we modeled it as 3 components. Each one has a fixed opacity. You can imagine modeling this as some functional form of mass as a function of opacity and doing something more complicated, but I'm not sure it's warranted.
So usually people argue that it's a great success of theory, that it matches the data, but the fact that you need 3 components makes the theory very ugly, and it's not at all clear that it's successful.
So I think the successful part here is that really there's no way to model this full light curve without having the R process opacities that people predicted from lanthanides, and the R process heating rates that people have predicted from nuclear physics calculations, independent of any data.
Okay, but could you fit any data that you would give the theories with
this kind of model? No. So this is not going to work for a supernova.
It will not?
No. Because the input heating rate for our process and for radioactive decay of nickel is completely different, right? And the opacities are completely different.
So the reason you wouldn't add a 4th component is that it might fit a little bit better, but the chi-square doesn't permit it or doesn't require it. But the 3 do pass some like F test or something.
Yeah,
right?
yeah.
But if he had better data, he would probably need another one.
It's possible. I don't know. But okay, so that's the light curves, right? I mean, that's the broad behavior. But let's look at the spectra, because here we have a lot more detailed information. So in addition to just measuring the brightness, we collected spectra in optical and infrared over a period of about 10 days. So the light curves go out to 1 month, but because the object faded very quickly after about 10 days, it was impossible to get spectra. So you can see this very significant evolution. So on the first day, there's this significant bump here in the blue part of the spectrum that just disappears, and the spectrum shifts to the red and develops features. Okay, so it's the same thing that we see in the light curves, this early blue emission shifting to infrared emission. So in the blue part of the spectrum, the optical part, we see this rapid fading. And the interesting part is that there are no spectral features that are detectable. Okay, it's overall just a fairly smooth, black body-like emission component. And the reason for that is that, and we already knew that from the light curve observations, that the velocities are really high, 0.3 c, and any spectral features that might be there are completely smeared out by just Doppler broadening. Okay, so we don't really see any unique spectral features, but it is giving us essentially the same view that we see from the light.
This is roughly the temperature of the sun. I mean, it's 6,000, 5,000.
Yeah, 5,000 Kelvin at early time, yeah. And then it cools very dramatically. So again, from 5,000 Kelvin down to about 3,000 Kelvin in the span of a few days. So a supernova, typically the temperature is more like 8,000 or 10,000 Kelvin, and it stays roughly that for 10 days or a couple of weeks. So very rapid cooling to red colors. So we can compare to pre-existing spectral models of this kilonova emission spanning a wide range of parameters, and what we infer from looking at the data is roughly 0.03 solar masses at 0.3 c, which is similar to what we found from the light curves. And overall, the evolution, 2.5 days, 3.5, 4.5 days looks pretty good. When we look at the earlier spectrum, so the other thing I forgot to mention is these orange lines, which seem to give the good fit, are for a lanthanide mass fraction of 10 to the minus 4, which is very low. In the solar abundances, lanthanide fraction is about 0.1 in the R process. But at earlier time, it looks like even that's an overestimate, and the emission is actually much bluer. So there is some gradient in the lanthanide fraction as a function of time. So at early time, it's close to 0, then it's about 10 to the minus 4 for a few days. Now, in the infrared, it's a different story. So here we clearly see spectral features. So this doesn't look like a black body. I mean, overall, it might have a black body shape, but you can see these peaks and absorption features and things like that. And the reason that we see that in infrared is because on these time scales, so this is after about 4 or 5 days, the emission is dominated by this component that has lower velocity. So we can actually see the individual, or we can see features. They're not completely smeared out. Okay, so here, again, by comparison to models, we infer 0.04 solar masses moving at 0.1 C with a lanthanide fraction of 1%. So significantly higher than what we found from the optical. Okay, so in the spectra, irrespective of what we infer from model fitting of the broadband emission, in the spectra we see directly the signature of this evolution from a low lanthanide fraction to a high lanthanide fraction. Okay, so what can we actually learn from all of this, right, from these optical and infrared observations? So first of all, we have direct spectroscopic evidence through the infrared spectra that there is actually R-process nucleosynthesis that's happening. These features that we see in the infrared don't match anything that we see in normal supernovae, which are dominated by nucleosynthesis up to iron peak elements. Okay, so but they do match the models for kilonovae, which are based on R-process nucleosynthesis. The amount of mass ejected in this event multiplied by the rate that's estimated from this one event, which is uncertain by an order of magnitude, matches our inference of how much R-process we need to explain the galactic R-process abundances. So what this suggests from the very high ejecta mass here is that neutron star binaries really dominate the R-process production, not supernovae. And we find these components that have a wide range of lanthanide fraction and different nucleosynthetic yields. Now, we can go beyond that, just the fact that there was R-process. So this blue component that has a velocity of 0.3 C is indicative of ejecta that comes from this collision, direct shock heating of material during the collision of the two neutron stars. Okay, so what we infer from that is that the two objects that merged were two neutron stars, not two black holes or a neutron star and a black hole. You need an actual surface, an actual collision. Okay. The other thing that's interesting is the large ejecta mass. So here are simulations showing how much mass is going to be ejected during this collision as a function of the neutron star radius. Okay, so if the neutron stars are smaller, you get more ejecta. And the reason is that the collision happens at higher velocity when the neutron stars are smaller. So we inferred about 0.02 solar masses from this component, which suggests small neutron star radius of about 11 kilometers. Okay, so that's a direct inference about the properties of the neutron stars that come from this electromagnetic radiation.
I'm just, can you rule out acceleration up to 0.3 C of material off of the remnant disk by a disk wind of some kind?
Yeah, the disk winds are usually limited to about 0.15 C or something like that. You can't get 0.3 C, and the reason is that it's just, it's a much larger structure. The escape velocities are much lower. So you don't really get this, I don't think there are any simulations that show that you can get anything close to 0.3 C. The dynamical ejecta can get to 0.3 C, but that is almost inevitably has a very high lanthanide fraction. So it's not going to give you this blue component. Okay, what else can we learn? So this red-purple ejecta that has 0.1 C, that is typical of accretion disk winds. And here, the fact that the lanthanide fraction is fairly high suggests that if there was a period of time when there was a neutron star before it collapsed to a black hole, that period of time was short, less than 1/10 of a second. And the reason is that if you have a neutron star that's sitting there for a long time, then the neutrino emission from the neutron star will raise the electron fraction of the outflowing material and will suppress the production of lanthanides. Okay, so that's kind of an inevitable outcome, and people have seen this in a wide range of simulations where they just let the neutron star arbitrarily live for a second, 10 seconds, 100 seconds, and you can see that as it lives longer and longer and longer, you essentially completely kill the production of lanthanides. So the fact that we see this material having a lanthanide fraction of about 1% by mass is telling us that the neutron star, if there was a neutron star phase, it was short, and therefore that the final product was a black hole. now people have taken this even a step further and actually combined all this information from the electromagnetic signatures, the ejecta masses, the lifetime of the neutron star, to place independent constraints on the neutron star equation of state from what's available from the gravitational wave data. So that's summarized here. So from the gravitational wave, sorry, I think this is the other way around. The gravitational wave data ruled out that had the tidal deformability parameter be less than 800. From the EM data, the argument is that there is a lower bound that's about 300 or 400. So it's starting to rule out certain neutron star equations of state, both on the gravitational wave data and independently of that of the EM data. So I think this is just starting to be an interesting game that can be played with future events, where we can start kind of carving out parts of parameter space, both from the gravitational wave information and independently of that from the electromagnetic information, in terms of the properties of neutron stars. Okay, do I have a couple of minutes?
Yeah.
Okay. All right, so let me talk about the radio and X-ray. So the radio and X-ray emission were detected, but not early on. So there were observations, our first observation, for example, in the radio was 2.5 hours after we found the optical counterpart. And it led to a non-detection. And in fact, the source remained undetected for about 2 weeks. And then it started brightening up. And same in the X-rays. So in the X-rays, we had an observation with Chandra 2 days after the event. There was nothing there, but 2 weeks after that, there was an X-ray source at that position. Okay, so what's going on here? So our initial interpretation was that we're essentially seeing the effect of the jet, which initially we're viewing away from the axis of the jet, but over time, as it slows down and spreads out, it can then become visible after some delay. And so this is a model, for example, of a jet viewed at different angles relative to the line of sight, and you can see that there is this initial period where the emission is not detectable, and then it starts rising, and that's a delay that how long it takes the jet to spread out and come into the line of sight. So by looking at the radio and X-rays, we concluded that we're looking at a jet somewhere between 20 and 40 degrees away from the axis of the jet. And we could also calculate what the properties of the jet were, and they were very similar to what we see in short gamma bursts. Similar energy scale, similar densities. Yeah.
Does this still stay if you assume it's a cocoon model?
So in the yes, you will get a delay. So in the case of a jet, the delay is because of the viewing angle. In the case of a kind of only mildly relativistic, more spherical outflow that people call a cocoon, the delay is because it takes some time for this cocoon to decelerate. Because it has a lot more mass, it doesn't decelerate as quickly as a jet. And so even though you're looking at it from all directions, early on you don't see any emission because it hasn't decelerated yet. So that delay is the kind of time scale to decelerate. Okay. So you can get a delay in both cases.
We have X-rays in different bands. Can we say something about the spectrum?
So the spectrum all the way from radio to X-rays, and so we can measure the spectrum between the radio and the X-rays, and then internal to the X-rays and internal to the radio is just a single power law the whole way.
Because a jet that expands sideways should show some spectral change as well.
Not really, because all this delay is just due to the dynamics, and so it should affect the emission at all. You should see the same behavior at all frequencies.
At all frequencies, but yeah. there is a break, a cooling break.
Yeah, so here we don't see any evidence for a cooling break. It has to be above the X-rays. Yeah. Okay, so with the first couple of observations in the radio and in the X-rays, we could say, okay, our very simplistic jet model where there's just one outflow, very narrow, can explain things. But there are now, so it's been 2 months since these papers were published, and we've been collecting more data. So here are new radio observations, and you can see that it's continuing to rise in the radio. There was just an observation a few days ago by Chandra, and these were the first 2 observations, and it got brighter in the X-rays as well. So in fact, what's happening in the radio and the X-rays is that the source is getting brighter, even though in the optical and infrared it disappeared. So now the story becomes a little bit more complex, because the original models of just a jet that has a very sharp edge cannot explain this continued rise. So what we need is either a jet that has some structure to it, angular structure, so it has a lot of energy in the core and some smaller amount of energy in the wings, or a jet plus a cocoon, or maybe these two things are just the same thing. I was at KITP in Santa Barbara last week, and we spent 2 days arguing about whether this and that are the same thing or two different things, and it started feeling like an argument about semantics. But you can see that now we can explain this by having, so this is, the model here now is models from Andrew McFadgen that have a jet propagating through in a neutron star binary merger done self-consistently, and it has structure, and they can explain this. Here's a paper that came out yesterday, I think, from Davide Lazzati, where they did simulations. So here's the jet, and here's all this structure around the jet. That's all, and what they're saying is what we observe is a combination of viewing contributions from all of these things. So most of the energy is here along the jet, but there's also material moving more slowly. So that's what I mean by jet plus cocoon or structure jet, is that it's not just a single direction. And you're seeing essentially, we're looking at it kind of 30 degrees away from the axis, and so we're seeing the combination of all these things.
But it seems on that one that if you wait long enough, you'll be able to test it. There'll be this downturn at a specific time.
Yeah. So in his simulations, that's what they're predicting for the continued evolution. Okay. So it will continue to rise, and it will get about 3 times brighter compared to where it is now. That's what is it?
Years.
That's about 2 years from now or something like that.
In terms of the energy, is there much less energy at late times, or more?
There's less energy per solid angle, but there's more solid angle. So you're getting more energy overall.
And it's still much less than the original energy that was released. Yeah. I mean, most of the energy was released early on. Yeah.
Okay.
Is this depend on constant jet driving, like a constant power from the jet?
No, so the jet turns off after about a second or two. So what you're seeing is just So so this is the prediction from this particular model. Now, if we observe it and it does something like that, then all you need to do is adjust this a little bit, and I'm sure the theorists can do that. There was another paper. So these are again the radio observations, and here they explain it not as a jet, but they say, okay, there is a cocoon. There's no jet. There's just a cocoon. But the cocoon has a distribution of Lorentz factors. So instead of, so you're saying the whole thing is overall spherical, but there's a little bit of material moving at high speeds, and then there's more and more material moving at slower speeds. So the structure is not angular, it's radial structure. And it can also explain the data. So I think there are multiple ways right now, at least, of explaining these observations, but it's one thing that's exciting is that this event we'll still be observing it in the radio and X-rays probably 2, 3, 5, maybe 10 years from now. Yeah, speaking of which, so the radio and X-rays that we're seeing now is from some sort of a relativistic or mildly relativistic component. All of this ejecta that's producing the kilonova, the 0.05 solar masses moving at 0.1 C, will also eventually decelerate and produce radio emission. And that's going to take even longer. So this is our prediction for what the radio emission from that is going to look like. And you can see that it will take about 10 years before we see that, somewhere between 10 and 20 years. So maybe we'll still be observing this thing into the 2030s. Okay, let me...
I'm sorry, I know you're like, we're running out of time, but this is very cool. We talked before at lunch about resolving this.
Yeah.
The size may be set, but would you expect to see structure? Would this be a double-lobed object at some point?
Yeah, not on the timescales where you'll resolve it, it more or less will kind of isotropize roughly. I mean, in the case of a jet, it might be a bit more asymmetric compared to just this cocoon idea. But I think that all of this is below the formal resolution of the VLBI.
Oh,
and
it is.
So
Okay.
I think then it becomes a more of a, you inject models, and yeah, I think it's going to be tough. I don't expect it will be really well resolved and where you can actually see 2 hot spots or something like that.
You wanted to go off in our galaxy.
Yeah, or like 10 megaparsecs, which eventually will have one. Okay, there's more to this story about the galaxy and about the Hubble Constant and all of that, but I'm already running over time, so unless people want to ask specifically on that, I'm always happy to talk about it, one-on-one. Thanks.
Questions?
Yeah, back to what you were just talking about with the long-term radio emission. So that obviously has a much higher duty cycle than the optical. I mean, can you look archivally for these things? Is there any unique features of them that you can...
Yeah, so we actually we had a paper on this in a broader context of, you know, is it possible to look for transients in general in the radio? And so the way we're doing now is we find supernovae, we find these kind of events, tidal disruption events, and then we go and we follow them up in the radio. Which is, can you just find them in the radio with big surveys? And the answer is that it's quite complicated for two reasons. One is that essentially in all cases you're seeing synchrotron emission from some expanding blast wave. And so one blast wave looks like any other blast wave, and it's hard to know what you're actually looking at. You can get the overall energy of the outflow, but it's hard to put it in context of what it is and what generated it. The other thing is that you can see here that, I mean, this is plotted on a log scale, which is really misleading because when you observe, you're not observing in log scale, you're observing in linear time. And there you can see that the time scale for it to go from, you know, its brightness, let's say, peak to just a factor of 2 below that is roughly the same amount of time it took it to get to its peak brightness. So you need a baseline of 10 years just to see something like that fade by a factor of 2, which would tell you that it's actually a transient source and not some steady source. So you need these very long time baselines, which we don't have yet.
And the X-ray is long gone by then? Or
the problem in the X-ray is that there are, I mean, there will be, what is it called? The new X-ray, German, Russian X-ray mission.
Linux.
No, not Linux. Eurosita, right? Which will do a big sky survey. But there too, the baseline is only, I think, 3 years, and most of the sky will only be covered once or twice. So there are no wide field, high time cadence X-ray surveys. There are no radio surveys like that yet. And it's the SKA will probably be the first one. And the rate of occurrence of these binary neutron star mergers is very low. Right? I mean, when LIGO finds it and tells you where to look, it becomes easier. But this is roughly 1 per million years per galaxy, or you know, whereas a supernova is 1 per 100 years per galaxy.
So they're that much more interesting.
Yeah, but you know, you need a big volume of space in order to find any of these.
I had a question about the identification strategy.
Mm-hmm.
So you said there were about 80 plausible transients, astrophysical transients, and you distinguish these by 10 days after only one had faded rapidly. Does this mean that you have to follow up that entire search area for 10 days or a few days at least? Or?
Yeah, so I think that's a good question. So originally our strategy was based, so this blue component of the kilonova, which turned out to be dominant here at early time, from a theoretical point of view, was much more speculative. The more robust part was that there will be this component that's very red because of the lanthanides. And so our search strategy was aimed at not only looking for something that fades quickly, but also something that's very red in color, much redder than a normal supernova. It may turn out that that's not a good discriminator. If all of them have this early time, very blue emission, then they're almost just as blue as any other supernova. And then you really will need several days of observations before you can convince yourself that you really saw.
So if there's a larger volume, then instead of 80, it's 1,000 candidates.
Yeah. I mean, it really could be non-trivial.
Great. Well, maybe are you sticking around for?
Yeah, I'm happy to stick around for a little bit if people want to ask questions.
Please stay.
Okay. Well, let's thank Guido again.